In this example, we're solving an equation which involves a modulus. We're going to look at two different methods. First of all, method one, graphically. We're going to draw both sides of this equation and see where the two graphs intersect. First, I'm going to draw the right-hand side. I'm going to draw y equals 2 take away a half x. Compare this with y equals mx plus c and identify the gradient and the y-intercept. So I've changed the order. I've written the minus half x first and then plus 2, so I can easily compare m, which is the gradient. So the gradient is minus a half and it goes through the y-axis at 2. So there we go, the line y equals 2 take away a half x. Just going to put it on where it goes to the y-axis and where it meets the x-axis. So I need to think about, when is y 0? Well, if x is 4, then y will be 0. So it goes to the y-axis at, the x-axis at 4. Now for the left-hand side of the equation, the modulus of 3x take 5. I'm going to draw the modulus of x graph first and then think about how it transforms. So if you're doing this on paper, I would recommend imagining what the mod x graph looks like in your head and then imagine it transforming, and eventually you'll be able to draw the final graph. So these red lines here are a very rough graph of the original mod x graph. Now the 3 will stretch it in the x direction with a scale factor of 1/3, which will look like it's been squashed towards the y-axis. So it'll get steeper, being squashed towards the x-axis, or the other way of describing that, it's been stretched away from the y-axis but with a scale factor of 1/3. So that's now the graph of the modulus of 3x. Now the take 5 inside the brackets, that would move it to the right, but not by 5. It'll be 5/3 because of the scale factor of 1/3 that's already happened. So this will move to the right by 5/3. So there's 4 on the x-axis. So it doesn't go beyond that. So it'll be around about there. I now need to check where will this go through the y-axis, just to make sure the graph is accurate, because I can see 2 on the y-axis. I need to make sure this point up here is definitely bigger than 2. So that'll happen when x is 0. When x is 0, we get the modulus of 3 times 0 take away 5, which is the modulus of 5, which is 5. So yep, I can leave my line where it is. It definitely is above 2. And it moved to the right by 5/3. So here x is 5/3, which is 1 2/3. So there's a reasonably accurate graph. It's still only a sketch because we haven't used proper graph paper and we never need to. But it gives us an idea of how many, well, it tells us how many solutions to expect. And we can see these graphs meet each other twice. Now it's a case of coming up with two equations that we can then solve to find those x values. We also know what our answers are going to look like. Both x values are going to be positive, and they're going to be either side of 5/3. So the green lines here, these are going to be our answers, our x values. Right, now for the equations. If we look at this portion of the mod x graph, or the mod of 3x take 5 graph, that is the portion of the graph from y equals 3x take 5 where y was already positive. In other words, the modulus had no effect. If I just drew the line y equals 3x take 5, this would be part of it, and it would just continue. Instead of bouncing off the x-axis, it would continue going through the y-axis at -5. So this segment here, this portion, has the equation y equals 3x take 5. We want to know, where does it equal the blue graph, which was 2 minus a half x. So to get, let's label these A and B. So B will come from solving 3x take 5, which is what this line has an equation of. Where does that equal the blue graph, which is 2 minus a half x. I'll solve that in a moment. Let's look at the other one. The other part of the modulus graph, that's the bit that was effectively flipped up or reflected in the x-axis. So this bit now has a gradient of minus 3, whereas this part had a gradient of 3. This part will have a gradient of minus 3. And we can see it goes to the y-axis at 5. So this part of the graph, gradient of minus 3, goes to the y-axis at 5. So solution A will come from solving minus 3x plus 5 equals 2 minus a half x. And I'm sure you can now solve those equations yourself. I'm going to pause the video and solve them and then check your answer against mine. So there we go, solving those equations, we get x values of 2 and 6/5. And looking at the graph, yep, they seem sensible. They are either side of 1 and 2/3. One is slightly bigger, one is slightly smaller. And they're both positive. So we can see those are looking like sensible answers. So there's the graphical method. Method 2, the algebraic method, is very similar, but you've just got to be careful with using the algebraic method because sometimes it gives us phantom solutions. So solutions that don't actually work in the original equation. So the graphical method has an advantage in that we can see how many solutions there are going to be. With the algebraic method, it might give us some solutions that don't actually work in the original equation. So you must check them if you're going to use the algebraic method. So with the algebraic method, we just look at the equation and we use something along the lines of this line of thought. If the modulus of A is equal to B, then the thing inside the modulus must be either the same as B or negative B. So using that thinking, in this situation, the thing inside the modulus must be either exactly the same or the negative of the right-hand side. Now the plus or minus could actually go on either side here, and you'll see we actually get the same two equations as the graphical method. Whereas with the graphical method, we know there will definitely be two solutions. If you're using the algebraic method, you must check both of these at the end to see if they both work. So I'm going to split this now into two equations. I think it just makes it easier to work with. So once with the plus, and then once with the minus. As I said a moment ago, it's just the same two equations as we had over here. The equation for point A, if you times both sides of that by -1, you get this equation over here. So they're going to lead us to the same solutions. We've already solved them, so just to save a little bit of time, this one gave us x was 2, and the other one gave us x was 6/5. Now for the bit that you must not leave out, check that they actually work in the original equation. You must do that if you haven't drawn a graph, because it's possible that one of these might not actually work. So let's put that in. If x is 2, the modulus of 3 times 2 take away 5, is that equal to 2 take away a half times 2? Is that true? So on the left hand side, inside the modulus, we've got 6 take 5, which is 1. So left hand side is 1. The right hand side, 2 take away a half of 2. So 2 take away 1, that's also 1. Yes, the equation balances. Let's try it now with the other value, 6/5. We already know it's going to work because we've seen the graph. But let's just run through it. On the left hand side, we've got 3 times 6/5, take away 5, which is 18 over 5, take away 15 over 5, which is 3 over 5. When you mod that, you've still got 3 over 5. On the right hand side, we've got 2 take half of 6/5, which is 2 take away 3/5, which is 10/5 take away 3/5, which is 7/5. I've made a mistake somewhere. On the left hand side, 18/5 take away, sorry, the left hand side was 18/5 take away 25/5. sorry, I said 15 fifths a moment ago. It's obviously 25 fifths, which gives you minus 7 fifths. When you modulus it, you do get 7 fifths, so they are both the same. So we know these two x values, they are definitely answers to the equation. So if you're going to use the algebraic method, please do not miss out that last bit at the end.